very complicated, but it provides a safe operation. So to talk about the non-isolated charger, the non-isolated charge has a high efficiency, as I mentioned, but safety sometimes is compromised. The isolated charger provides safety features, but again, the efficiency becomes low because you usually involve three-stage power electronics devices. Okay. The control, the charging of battery needs to be controlled, and the batteries themselves already have a BMS. So, interface between BMS and the charger is very important. The communication is usually done through CAN, computer area network. And the battery control unit, or BMS, sometimes also called battery ECU, they communicate with the charger. They also communicate with the hybrid vehicle ECU, so that in operation of the vehicle, the battery ECU mainly communicates with HEV ECU. But when the vehicle is stationary, when you charge the battery ECU will communicate with the charger to control how the batteries are controlled. In a PHEV or HEV system, at 300 to 400, 500 volt system, there are a number of batteries in series. Typically, if you use nickel metal hydride battery for HEV, you're going to see 30 to 40 battery cells in battery modules in series, and each module has 5 to 6 battery cells. So you see a few hundred, 200 to 300 to 400 battery cells in series. In a lithium-ion battery pack for PHEV, each cell is about 3.65 volts for lithium iron phosphate battery, and a little higher for some other chemistries. For a 300 to 400 volt system, you're looking at about 100 cells in series. So there are a number of batteries in series. As we mentioned earlier, if you want to do balancing, you need 100 balancing circuits to be connected to each battery cell, or if each row sometimes may not be a single cell. It may have a few cells in parallel. In that case, you form a row, which is equivalent to a large battery cell. And your BCU, battery ECU, your BMS, needs to be able to communicate with all those battery cells. Therefore, each cell of the battery, or each row of the battery, needs to have a controller. And that usually is called a cell monitor, a cell module monitor, CM. A charger needs to know what happens to each row, so that it can change the charging current, so that you don't overcharge any cell in the large battery system. So it's very important. So this is sometimes called a rule-based charger. What it means is that the row voltage would decide how the batteries are charged. So the charge is controlled by row voltage instead of the whole string voltage. The rule-based charging, as I mentioned, that because the batteries are put in parallel in series, when the rows are in series, they're placed in different places in the pack due to chemistry inconsistency, temperature difference, and the row voltage can be different at the times. So therefore, the charge needs to respond to the row, and that is usually communicated by a BMS system. When you build a PHEV, there are a lot of things that you can do in addition to just the electrical driving range and the fuel economy improvement. The things that we can do would include, for example, cold start emission reductions, okay, and cold weather performance improvement, V2G, and some other things. So let's look at one thing. How do we improve the cold emission of a PHEV? How to improve the cold weather performance of a PHEV? I'll give you some little bit background information before we actually talk about the PHEV performance improvement. In cold days, a conventional vehicle that has an internal combustion engine would generate a lot of emission in the first 2 minutes of the driving cycle. So if you look at a typical driving cycle, that's about 1,400 seconds. If the weather is cold, in the first 120 seconds, about 10% of driving cycle, you're going to emit roughly 80 to 90% of the total emissions, of the emission that is generated within the total driving cycle. The reason is all the vehicles are equipped with a catalyst converter. That catalyst converter is a tailpipe processing unit. That's the unit that can reduce the emissions from the engine tailpipe, okay, from the engine. But those catalytic converters only work when they warm up, when they at a fairly high temperature. But when you start the vehicle in cold days, the catalyst is cold. Because they are cold, they don't function very well. So you cannot process the emissions from the engine. Therefore, you have very high emission. In the past 20 years, people have developed some methods for cold weather emission improvement. For example, catalyst heaters. But the problem is to keep the catalyst warm, you need roughly 3 to 5 kilowatts. And you need roughly 5 to 10 minutes. The problem is that we don't have the patience to wait for 5 to 10 minutes before we drive the vehicle. We get out in the morning and we want to drive the vehicle right away. So we don't have, even though we have that system available, but it will never be popular because people are not going to use it. So there are some other methods that may be expensive to implement, or they have some other things. So overall, the cold emission is still an issue in conventional vehicles. A couple of years ago, when HEV become available, people have some idea saying, because HEVs normally will start with the motor without starting the engine to drive for like a few minutes, so why not use the battery to warm up the catalyst while we're driving the vehicle? And that was a good idea, but it turned out that it's not possible because in cold days, those battery energy will drop significantly. When the energy drops significantly, you don't have a chance to drive the vehicle with the battery, and therefore you don't have a chance to warm up the catalyst. So therefore, in a HEV, you still have the cold emission issues. So you will see all the HEVs in cold weather, when you start the vehicle, the engine will be started right away because energy don't have much, the battery don't have much energy available in cold weather. So that issue still remains as an issue. So we want to look at this in PHEV, and that has come up because we are saying that with a PHEV, you have a much larger battery pack, a lot more energy. Can you do that same thing you couldn't do in HEV? Well, it turned out that it is still difficult. The reason is when temperature drops below 20 degrees C, the energy in a lithium-ion battery pack drops so much that they drop 60 to 80%. So even though you have an 11 kilowatt pack, but you don't have enough energy. In the meantime, because of cold weather, the battery power is also highly affected. Therefore, you don't have enough power to drive the vehicle. So without proper management, a PHEV can also not deal with the cold emission problem. Not only that, the driving range, the electrical driving range, are also limited because of the cold temperature. In order to deal with this issue, and many people have looked into this, and we have been discussing to design, let's look at the diagram. We're going to design a battery cycling technique. So what it means is that when you charge the battery in cold days, when the battery is close to be fully charged, don't disconnect the charging. Maintain the battery charge at a small current, so the batteries will be still warm in the morning. So that's one thing you can do. However, if you maintain small charge, when it's fully charged, you have to take the energy out, otherwise you have to stop. So if we have a bidirectional charge, we can take a little bit of energy out of the battery, And then the next 5 minutes, you charge the battery. So you keep charge and discharge the battery at 1, 2, or maybe 3% of SOC. So just to keep the battery warm in cold days. So in the morning, when you start to drive the vehicle, you have energy available. So that's one thing you could do. Another thing you could do is that you can design a thermally insulated pack where you can keep the battery warm inside. Once the battery is warm inside, you can have enough energy in cold days. And the thermally insulated pack is also good for hot temperature operating conditions because, for example, in Arizona, if you have a battery pack that is not thermally insulated, the battery can get as hot as 60 degrees C, and which is the temperature that the batteries are not going to perform. If you want to cool the batteries down to, let's say, 30 degrees C, which is good for the battery to be used, it's going to take hours or 2. Therefore, you don't have a chance to use the battery whether it's really hot. So what are you going to do? Again, you design a thermally insulated pack, except for the cooling channel where you have cooling media exchange between the outside. Otherwise, the batteries are secured inside the thermally insulated pack. And we did some simulation. It showed that if you do a good thermal insulation, it takes about 24 hours for the battery temperature to go from 25 degrees to 55 degrees C. Or it takes about 24 hours from 25 degrees C to go down to minus 10 degrees C. Therefore, you can maintain the battery temperature for at least 24 to 48 hours. You will have energy to drive the vehicle, even during cold days. At the meantime, since you have so much energy available in the battery pack, we could design an auxiliary heater to heat up the catalyst converter. Once the catalyst converter is warm enough, we can start the engine to significantly reduce the cold weather emissions. So this is something that can be done, but in order to do that, we need to design a thermally insulated pack, and we need to do a good thermal design and good insulation materials and good packaging. So this is something that you have really to deal with the thermal insulations and so on. A good design would couple electromagnetic, electrochemical, and electrothermal, and design and modeling, experiment, verification, validation, until at the point you're going to get a really nice functioning system. So let's take another break.